Hello, everyone. Welcome back to Codex. Our talks this summer feature graduate students and postdocs who were nominated to speak by their senior colleagues. Today, we have Kaysie Rose, who is a graduate student at Iowa State University. She will tell us about dimension counting bounds for equi-isoclinic subspaces. Take it away, Kaysie.
Awesome. Thank you, John. Thank you also for all the help making this talk come together. Just really messing with some details, making it great. And thank you to the organizers for the invite. I've come to Codex for a while. Happy to be on the other side. So we're just gonna get right into it. And yeah, please ask questions as we go along. So this is joint work with Joey Joseph W. Iverson, my PhD advisor. Um, there's a preprint of this paper that you can find on the archive. It's been on there for a while as a preprint, so hopefully it'll be a postprint soon. This talk is a strict subset of the results in that paper. So if you're interested in a little more of this sort of thing, please do go check out that paper. There's some cool stuff in there. Cool. So here is our big core key question of the entire talk. How many equiangular r-dimensional subspaces can we fit in F to the D? And the word equiangular is in red because that is not the right word. I'm lying to you. We're going to use a slightly different word, but the idea you should think is equiangular. The word we're actually going to use is uh, equi-isoclinic. We'll talk about the definition of that in a bit. It's just an extension of equiangular to higher dimension things. So what are those equi-isoclinic subspaces? We're going to look at an old bound of Lemons and Seidel. That's never been achieved. We're going to explore a strategy that gives us actually a sequence of bounds, the titular dimension counting bounds. And then we're going to look at the last bound in the sequence, and we're going to see that it's maximal in an interesting way. So, part one. What are these equi-isoclinic subspaces? We're going to start with the easiest example, equiangular lines. So equiangular lines are just one-dimensional subspaces where pairwise the acute angles between them are equal. So here I've got three lines in two real dimensions, and this red-blue angle, this blue-black angle, and this black-red angle, they're all equal. They're all, I believe, pi thirds. Over here, it's a little harder to see. I've got six lines in three real dimensions that are also equiangular. A classical question that a lot of people have thought about is what's the largest number n of these equiangular lines you can fit in a fixed dimension? Here, two real dimensions should not be too hard to convince yourself that three is the best you can do. And in fact, I think if you take a pen and paper and just kind of scribble for a minute, you'll probably work out the proof, or at least a sketch of the proof. This one, six lines in three real dimensions, is trickier to prove, and it only gets worse, right? So this is a classical question, um, and one of the better resolutions to it is an upper bound, called Grothendieck's bound. So if you think about frame type stuff or systems of equiangular lines, this is going to sound really familiar. If you've got n equiangular lines in F to the D, and we're only concerned with R or C, you get this upper bound on the number of lines you can have. And in a sense, this is a decent to good bound. Over the real numbers, it's achieved a small handful of times, and it's conjectured that that's basically it. Over the complex numbers, it's achieved for a lot of small d. We know it up to like, I want to say around 200. And it's conjectured, it's Zauner's conjecture, it's famous conjecture, or at least I hear about it a lot, that it works for all d. So, okay, at least sometimes tight in the real case, possibly a perfect upper bound in the complex case. We want to do this sort of thing, but instead of lines, we want to do planes or 3 or 4 or arbitrary dimensional subspaces. So if we want to generalize equiangular, we need to generalize angle. And the right concept of angles between subspaces, it's not really obvious, is this thing called principal angles. So if you have two one-dimensional subspaces, two lines, morally, or as far as we're concerned, there's one angle between them, the acute angle. We're not really concerned at all with its supplement. So morally, we would want two r-dimensional subspaces to have r angles between them. And the way we get those r angles is this recursive process, which we're not going to worry about too much, but we're just going to take a look. So you find the smallest angle. In this diagram, the two subspaces intersect. So it's going to be this, just going to be 0. You take the vectors that achieve it. So here, this purple vector is it's both the vector in V and the vector in W. You go to the orthogonal complement, you find the new smallest angle, and then you just repeat the process until you run out. It's a bit tedious, but it works. And it gives you these principal angles, which again, I'm kind of asking you to take on faith that this is the right idea of angles between subspaces. They are like these are like the invariants of global rotations and scaling stuff. Or if you're interested, if you think about like metrics between subspaces and the Grassmannian and stuff like that, every metric on the Grassmannian is actually a function of the principal angles. So they do represent like a fundamental thing. Um, so those are the angles between our subspaces. We call subspaces equi-isoclinic if all of the principal angles in a sequence of subspaces are the same. So two pictures we've already seen. On the left, we have 3 pairs of angles, and each of those pairs has one angle. This one's equi-isoclinic because the only angle that pops up is pi thirds. Over here, we have one pair of subspaces, and there are 2 angles per pair because subspaces are 2-dimensional. And this is not equi-isoclinic because theta 1 is 0 and theta 2 is not. So if I have n r-dimensional subspaces, I'm going to get in total n choose 2 times r principal angles. And to be equi-isoclinic, I need every single one of those to be equal. A slightly awkward thing is that the first real non-trivial example of equi-isoclinic subspaces happens in R4. If you take these, an easy way, it's not the best one, but an easy way to get some is if you take these 3 guys, write them as vectors, and tensor them with the 2x2 identity, it's gonna blow up and it's gonna give you something. It's gonna give you some 2-dimensional subspaces of R4 that are equi-isoclinic. Turns out you can actually get 4. It's not here nor there. Cool. All right. Before we really get into things, I just want to talk about some notations, some conventions I'm going to be using in this talk that are not really going to be, they're a little fuzzy. I'm not going to draw any distinction between subspaces, orthonormal bases for subspaces, or isometries for subspaces. And when I say isometries, I mean, tall, skinny matrices where the columns of the matrix are an orthonormal basis for the subspace. Also, equi-isoclinic is a property of subspaces, of sequences of subspaces. If I ever say something silly like projections are equi-isoclinic or orthonormal bases are equi-isoclinic or anything like that, I just mean the underlying subspaces are equi-isoclinic. So this picture we just saw And this matrix that has three columns, where each column is an orthonormal basis for one of these, I'm not drawing a distinction here. Um, in fact, I'm really gonna be thinking about matrices. I do matrices, I go to my office, and I multiply matrices, and that's what we're gonna do in this talk. Cool. So here's some motivation, right? Why do we care about this problem? The subspace packing problem is something that a lot of people think about. How can you get n subspaces of R dimension in R to the D or C to the D? How can you pack them without having them be too close? How can I spread them out? So we want to maximize the distance in the projective plane. Um, it's bad if they intersect, right? They're as close as possible. I am touching you. And it's good if there's something like this, right? I can put whatever I want in these asterisks and whatever I want in these asterisks, and I get things that are orthogonal. But obviously, once you have too many subspaces, they can't be orthogonal. And it turns out that being equi-isoclinic is a good thing in this scenario because the sharpest angle that we're worried about up here is the first principal angle. And to make that as big as possible, it is helpful to be equi-isoclinic. Because if you're not equi-isoclinic, then you're kind of wasting space, right? If your first angle is pi over 100 and your last angle is like pi over 2, then maybe you could have, maybe you could have wiggled a little bit to be a little bit more productive. So equi-isoclinic is useful in this scenario. Um, there's this idea of equi-isoclinic tight fusion frames. If you're familiar at all with equiangular tight frames, this is one of the ways you can blow that up to talk about subspaces. So take some O and B's. You get this coherence condition where kind of the best you can do is getting this guy here. And this only happens, equality only happens in this bound when one, you are equi-isoclinic, and two, you meet this tight fusion frame condition. So this sum of projections is a constant times n. Equi-isoclinic is, well, this is the one we're focusing on here. If you're interested in tight fusion frame stuff, you're interested in equi-isoclinic. Okay, now we're motivated. Let's keep going. The definition of equi-isoclinic that we have is a bit awkward to check from the definition because we have to check n choose 2 times r principal angles. So we're going to be using from this point on the following equivalence of Lemons and Seidel, which is essentially we can evaluate isoclinic via this multiplication of the isometries of the OMBs. And that's nice for us. That's easy to check, relatively speaking. We can just multiply matrices. Multiplying matrices is what I do. So from here on out, this red condition is going to be how we evaluate equi-isoclinic, how we think about equi-isoclinic. So let's look at an example. It took me forever to align this, so I hope you appreciate this example. Here are 4 subspaces in 4 real dimensions. They are equi-isoclinic, I will tell you right away. And all we have to do to check that is 4 choose 2 equals 6, somewhat tedious multiplications. So start with the first 2, just plug and chug. This multiplication is really not that bad because you can see, okay, we just pluck off the top. This is going to give you, I believe, 1/3 times I2. And we want all these other multiplications to give us that exact same thing to be equi-isoclinic. So 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4. And as long as all those pairs come out to the same thing, alpha squared times identity, the same alpha, we win. We're equi-isoclinic. So it's not ideal, right? It's a sort of thing you could toss to a computer, you know, or I don't know, someone who's okay doing tedious work and say, yeah, go check if these are equi-isoclinic, and then they spend a while multiplying matrices and Cool. Um, we're kind of going to shift now. That's our background. We know what equi-isoclinic subspaces are. Now we're going to start looking at bounding the number of them. And again, I use this word equiangular because it is kind of the idea. So if you don't have what equi-isoclinic means locked into your head, if you mentally replace it with equiangular, you'll get most of the idea. So let's look at this old bound. We're going to try and beat it, right? That's the idea. So this is a theorem of Lemons and Seidel. If you have n equi-isoclinic r-dimensional subspaces of f to the d, you get this upper bound, where up here um you're taking that bound from earlier, that Gerson's bound, and you're just subtracting something that depends on r. You're just subtracting something that's OR squared. And if you think about it intuitively, that feels way too big. Right? It feels like, okay, if I go from r equals 1 to r equals 2, I'm doubling the size of my subspaces. It feels like I should probably be really chopping down the number n that I have. And in fact, Lemons and Seidel, they were not satisfied with this bound. This is a quote from that exact paper. They don't know whether this upper bound is actually reached for any r greater than 1. They have reason to believe this bound is too large. So this is what we're chasing. This is a bound that stood for 50 years, that was never tight, and we're going to try and upgrade it and find a tight improvement on it. To do that, we're actually going to take a lot of cues from the strategy that they use. So we're just going to take a quick look at the sketch. You take an equi-isoclinic sequence, and then you take a big sip of water. These are isometries, so if you do this move, you get the projections onto the appropriate subspaces. They're going to define this K1. It's a real subspace that is currently redacted. It is top secret. The projections, it turns out, are linearly independent in K1. So we have n linearly independent things in a subspace. N is bounded by the dimension of the subspace. And it turns out that dimension of K1 is this exact. So this is the strategy that Lemons and Seidel use. I think it's pretty slick. I think it's a pretty slick proof. We want to build on it. And the way we're going to build on it, we called this K1. Lemons and Seidel did not. We call it K1 because we're going to have a K2. In order to get to K2, in order to talk about K2, we're going to need to see what properties K1 has that we care. So to get our new sequence of bounds, we have to digest K1. So the properties in that proof that K1 needed, you start with your equi-isoclinic sequence. It needed to contain all of the projections onto the subspaces, and it needed to be a real subspace of FD by D, because that's where those projections live. And if you go through that proof of Lemons and Seidel, these are the two properties of K1 that they use. This is it. They define K1, they show it has these two properties, and then the proof just falls into place. So, what does that mean for us? Any subspace that meets properties 1 and 2 gives an upper bound. So you could get a really silly upper bound by just saying, I'll take all of the real span of FD by D to be my subspace. That would win. It wouldn't beat the bound Lemons and Seidel got. It would win. If we get a smaller subspace than Lemons and Seidel did, on the other hand, we get an improved bound. So we're gonna try to improve on this K1 that Lemons and Seidel have. So we call these corner matrix spaces. K1 is what we call the first corner matrix space. Let's see what is hiding behind the gray, not black, gray box. It's this. It is all D by D matrices M that 1 are Hermitian / self-adjoint, and 2 satisfy phi 1 star M phi 1 is in the real span of the identity. And do remember, this is a real subspace. Complex Hermitian matrices are not a subspace in general, but they are a real subspace, so that's why we have that condition. And the reason this works, right? All 3 of these conditions are going to be helpful. So obviously, if we're trying to catch the projections, obviously they are in FD by D. If we're trying to catch projections and make a small subspace, famously projections are self-adjoint. And then this green condition, right, is the one I think that's like, okay, what's going on there? It's actually quite clever. If you're isoclinic to phi 1 to the first subspace, your projection M is going to satisfy this. Because either you are a different subspace isoclinic to phi 1, in which case this multiplication is alpha squared IR because of, right, that's the equi-isoclinic condition we saw around slide 10. Or you're just the same subspace. The same subspace, it's kind of, it's isoclinic in a silly way, right? But if you plug in the same subspace, hey, this is an O and B, it just multiplies out to the identity. So in either of these cases, we get that this lands in the real span of the identity. So this captures all of the projections onto any subspace isoclinic to phi 1. So the way we're going to build on it is we're going to take advantage of the fact that, hey, we have more subspaces here than just phi 1. So if you imagine we have an equi-isoclinic sequence, and we've got some other O and B psi, it holds that psi is isoclinic to our I isometry number I, if and only if the projection that psi gives lands in this space. First condition, second condition, phi I star M phi I in the span real of the identity. This is an if or only if whenever psi is an O and B. There are things in here that are not projections that do not decompose in this form. But if it decomposes in this form, it is isoclinic to phi I. So we're going to take advantage of these 2 things and of the fact that we have more than one subspace, and we're going to define this Kj to just be, hey, take those things, intersect the first j of them. And what's going to happen when we do that, this was a condition being isoclinic to phi I. The projections that are isoclinic with phi 1 and phi 2 and phi 3 and phi j are all going to be in Kj. And this Kj is what we call the jth corner matrix space of the sequence. It is defined in terms of the sequence. That is something we're going to have to be careful with. This definition is maybe a bit is maybe a fair bit being thrown at you. Basically, the idea is we're coming up with a subspace that catches the projections onto things that are isoclinic. So here's properties we proved of this thing. You can check it out in the paper. If you have quarter matrix spaces of an equi-isoclinic sequence, um, you're going to catch the projections. Those projections are going to be R linear independent. So you get this. N is at most the dimension of Kn is at most the dimension of Kn minus 1, all the way down to the dimension of K1. So if any of these inequalities are strict, I hit forward too fast. I thought this said something different. If any of these inequalities are strict, then we can improve the lemmas inside L bound. But an issue we could run into here, this definition, it depends on the isometries that we started with. And if the definition of the space depends on the isometries, we can't know for certain that the dimension doesn't. So before we can try and beat lemmas inside Del, we have to solve this issue. And the way we're going to solve it is this classic normalization lemma. Basically, you give me an equi-isoclinic sequence, spinning it isn't going to cause any issues. It's not going to change the angle. Likewise, choosing new orthonormal bases for the same subspace, it isn't going to mess anything up. So we can always choose the first subspace, the first isometry, to be this really, really nice thing, where it's just the R by R identity, and then as many zeros as necessary. We can always choose the second isometry to be this slightly less nice thing, where it's alpha IR on top, and then this beta is just what it has to be for this to be orthonormal. So beta is square root 1 minus alpha squared. So we get this. And then after the second one, we've kind of run out of ability to rotate the isometries. We can pick a nice orthonormal basis to get alpha IR up top, but this xj and this yj are kind of a black box. I say kind of a black box. There are some properties we know of them that are explored in the paper, but they're really kind of, they're not like, oh, it's something times identity. They're like xj is invertible and it's of the form like scaled unitary plus something. Not super helpful. But we get one great isometry, we get one decent isometry, and then we get the rest are less than ideal. And with this, we can start. We can no longer need to worry about the corner matrix spaces being different up to a point, because every equi-isoclinic sequence has the same first isometry and essentially the same second isometry. It turns out that the choice of alpha is not going to matter unless you choose like I forget which one is bad. Zero or one is bad, but that's silly anyways. Cool. Let's see what K1 looks like. So I've done my normalization. I have that phi1 is the R by R identity, and then as many zeros as I need. So K1 is this. Looks like a lot, but we're just gonna break down what happens. So this red square represents all D by D Hermitian matrices. We're thinking of it in like a degrees of freedom sense. So if I only had, I was gonna cover it up with my hand, you can't see that. If we only had this red condition and none of this other stuff, we could pick any D by D Hermitian matrix. The blue condition is going to take away some of our free variables. What this evaluates to is it is just the upper left R by R block of M. So, suddenly we can't just put whatever we want in this block. I cannot have a 1 here. That is illegal. So we subtract the free variables that come from the blue square. But, sorry, uh, I make noises of surprise. I hit the button twice. But, um, we have to add back in one free variable because we are allowed to land in the span of the identity in that blue square. So red's free, we take away blue, but we add back in green. And this visual, this postage stamp visual, is why we call them corner matrix spaces, because whether or not you're in it's determined by the corner. It is determined by this corner. So let's see what the dimension of K1 is based on that visual. The dimension of D by D Hermitian matrices as a real space is just this. The dimension of R by R Hermitian matrices as a real space is this. And the dimension of IR as a real space is 1. So we really do just get exactly the bound that Lemons and Seidel had. Red minus blue plus green. So that's K1. That's the easiest one. We haven't beaten Lemons and Seidel yet. To beat them, we need to go to K2. So we're sticking with our normalization. So in that case, phi 2, it's alpha identity, beta identity, 0. And what K2 really is it's what we just had intersected with an additional condition. So it's intersected with this additional condition that now phi 2 star M phi 2 has to be in the span of the identity. This was already a condition, and this, well, obviously that was already a condition. So we're going to start with K1. I faded it out. These red squares, they are totally free. Or subject to being Hermitian, they are totally free. So you can put whatever you want in those red squares. But if you do the multiplication, they determine the dark blue square. So we subtract the dark blue degrees of freedom, except, just like before, we are allowed to be in the span of the identity. So we add back in a green line. So we actually subtract and then add back in the exact same amount we did in the original. So if we go, let's look at the bounds we get. This is the bound that was standing, the Lemons and Seidel bound, the dimension of K1. Red minus blue plus green. The dimension of K2, it's red minus twice the blue part plus twice the green part. It follows the pattern that we saw visually on the previous slide. We're going to go one more. The dimension of K3 is going to repeat that pattern one more time. Red minus 3 blue plus 3 green. I'm not drawing a visual of this one because it is not a pretty visual. I'm not even sure if we can visualize it. But this is what we get. And I've highlighted this one in red because it is our ultimate bound. It is our ultimate's the wrong word. This is the general bound that always works that we are presenting. This is the upgrade to this bound. If you were writing down this bound and you're like, wait, there's a better one, this is the one you should use. The question we asked earlier, pardon me, can we do this tight? Is this tight? The answer is yes. This is actually the same example we saw around slide 10. It is an equi-isoclinic type fusion frame, so it's equi-isoclinic. D equals 4, R equals 2, N equals 4, and it satisfies n's the dimension of K3. So we can find an example where this is tight, which is great. You might notice this is a little bit low dimensional. That's not a coincidence. And now maybe the question you're asking is, why is she sticking with K3 as the best bound? Isn't there a K4? It turns out this strategy breaks at K4. If you normalize the isometries, the dimension of K3 is totally invariant, but the dimension of K4 is not. In fact, this difference could be as little as 0, or it could be the maximum decrease we saw earlier. And we're pretty certain it could be anything in between. This is a quick example that you don't have to think too hard about, but take an EITFF 424, add a row of zeros, dimension of K4 is 9. Take an EITFF 525, toss one of those isometries away, dimension of K4 is 7. Those both have d equals 5, r equals 2, n equals 4, but their dimension of K4 is different. You do not need to internalize what's going on here. The point is just the dimension of K4, it can't be a function of drn in the way that the dimension of K1, K2, K3 was. So that's bad. We don't like that. Why does this happen? Right? Why is K4 the problem child? It comes ultimately from the normalization lemma. When we're working with K3, we have one of those meh isometries, one bad isometry, and we're just barely able to control what it does. But when we go to K4, we get two bad isometries. And not only do we get two bad isometries, if you try to find the dimension of K4, you're going to multiply them together. And I hope you don't mind my algebra here, but in my opinion, bad times bad is really bad. I know that sometimes bad times bad is good. Here, I assure you, bad times bad is really bad. So looking at K4 isn't going to work. If there's a way to continue this strategy past 3, we're gonna have to do something different. We're gonna have to find a new innovation, a new strategy, a new idea. So instead, we're gonna get a little bit of more juice from the squeeze by flipping the cereal box upside down. We've been going K1, K2, K3. What happens if we look at Kn, the last corner matrix space? Spoilers, it's going to be maximal in a way. It is going to be a maximal thing. So why do we even want to look at Kn? If you think back to the definition of Kj, it was defined in terms of the first j isometries. So if you give me 5 isometries and I say I'm going to go look at K3, I'm not even looking at 5,4 at all. I'm not even looking at 5,5 at all. I have essentially thrown them away. Kn, though, it doesn't throw away any of the subspaces that we hand it. Kn uses completely every piece of information that we give it. And if we achieve equality in the dim Kn bound, in the last bound, we do get some good properties. We get automatically that we're a tight fusion frame. So we automatically achieve that Welch bound. We automatically have the best possible coherence. The reason why that is just, hey, the identity, the full identity is in Kn. Well, if dim Kn is n, the projections span Kn. So you have to have some linear combo that equals that. And if you're equi-isoclinic, the coefficients are already equal. So meeting this condition, dim Kn equals n, the last corner matrix space, generalizes maximal ETFs in a potentially interesting way. We're gonna drum up some examples where this happens. This is the same example that we've seen about 4 times. And it turns out this is the smallest, nicest example of dim kn equals n. This is an eITFF 424 with n equals 4 equals the dimension of K4. So this is automatically an eITFF, and it's an interesting class of things. We want to do a little better than that. And what we're actually going to do is we are going to construct an infinite family of such things. And to do so, we have to interact with what are called the Radon-Hurwitz numbers. Basically, you write R like this, you factor out the even part, and you kind of write it like mod 4. And then the Radon-Hurwitz number is this kind of confusing looking expression. You don't have to memorize that, but we're gonna use this value. And it turns out what this is, the definition of this, it's the max dimension of a subspace of FR by R that is all scaled unitaries. And I do think this is kind of interesting that this value is this. Because I think if you asked me on like a linear algebra exam, if you asked me what's the max dimension of a subspace that's all scaled unitaries, I think my gut answer would be maybe 3. But it turns out that actually you can grow that kind of logarithmically with the even part of your subspace, of your dimension. So a weird thing to connect, but we are going to connect it. And we get this theorem. Any R, there is a complex eITFF where the ambient dimension is twice the size of the subspace with dim kn equals n. And that n depends on that row. If R is 2 to the k, every eITFF, C or R, that has this n has the dim kn equals n property. Has to be maximal if you have this n in this case. And something really nice about this proof, about this theorem, is if you delve into it, it is constructive. We do construct it in A. Basically, what you do is you take a simplex in that subspace of scaled unitaries, you arrange it in a good way, and then you do a bunch of tensoring to blow it up to whatever size you need it to be. And then we can also construct things that satisfy B. And in fact, for any R, there is going to be at least one. So we get this infinite family of maximal eITFFs, which is really cool. That's not really something that is floating around in the ETF case in the same way. But we get an infinite family of maximal eITFFs. Pretty neat. Some quick housekeeping on that. Why does this work? D equals 2R, so subspaces take up half the dimension of your ambient subspace. That is the nicest case for equi-isoclinic subspaces. That is the case where we always know the maximum n, and we always know how to construct it with this row space tensor shenanigans. Those hypotheses we just saw, you do actually need them. There are examples where D is 2R, but the dimension of Kn is not n. So it's not good enough just to satisfy D equals 2R. And finally, we don't currently know any equi-isoclinic sequences where D is not 2R and dim Kn equals n is satisfied. We certainly don't know of another infinite family. We have some weird stuff like some infinite families where this doesn't happen. If D is 2R plus 1 and R is even and you're in the reals, you know that this can't happen. But But yeah, so that is
Hey,
kind of
sorry. I think that's incorrect. I think that la third thing is incorrect. I think that we do know examples where the dimension of kn is equal to n and d is not equal to 2r. And I
oh,
think there are some in the
sweet.
paper. I just wanted to put an asterisk in the recording. I, I think if you look in the paper, it settles it.
Cool. Okay. Apparently, we do know examples. Joey, am I correct that we don't have any infinite families the way that we had infinite families for d equals 2r? Or do you not know?
I don't know of an infinite family. I think we suspect that there there's a family we have our eye on that we suspect this might be the case for.
Cool. All right. We've got the asterisk. We're not aware of any infinite families with d not equal to r where this happens. Cool. So that's pretty much, I'm coming up on the end here. The key ideas here, we used old tricks of Lemons and Seidel to get a new bound. That strategy works great until you hit the devious number 4. If you want to keep going past that, you're going to need a new technique. And if we go to our last corner matrix space, we get this interesting new generalization of maximal ETFs. So that is what I have. Thank you very much for listening. Organizers, thank you for the invite. John, thank you for working with me all summer to help make this talk come together. I really appreciate your input. Really feel like we made this shine, and then it wouldn't be a graduate student talk without the shameless plug. I plan on graduating in the spring. I am officially on the job market for postdocs and so on. This is my email address, and this is my website. Cool. Thank you.
Cool. Thank you. And as everybody's already doing,